Welcome to this presentation. Today we are going to see about the physical structures of a data communication network. A network is two or more devices connected through links. A link is a communication pathway that transfers data from one device to another. For visualization purposes, it is simplest to imagine any link as a line drawn between 2 points. For communication to occur, two devices must be connected in some way to the same link at the same time. And there are two possible type of connections, that is point-to-point and multi-point. A point-to-point connection provides a dedicated link between two devices. The entire capacity of the link is reserved for transmission between those two devices. Most point-to-point connections use an actual length of wire or cable to connect the two ends, but other options such as microwave or satellite links are also possible. When you change the television channel by infrared remote control, you are establishing a point-to-point connection between the remote control and the television control system. A multi-point is one in which more than two specific devices share a single link. In multi-point environment, the capacity of the channel is shared either spatially or temporally. If several devices can use the link simultaneously, it is a spatially shared connection. If users must take turns, it is a time shared connections that you can see in this diagram. And now let's move on to the physical topology. The term physical topology refers to the way in which a network is laid out physically. Two or more devices connect to a link and two or more links form a topology. The topology of a network is the geometric representation of the relationship of all the links and the linking devices. Usually they are called as nodes. And there are four basic topologies possible. One is mesh, star, bus and ring. And now let us have a look into the mesh topology. Right. In mesh topology, every device has a dedicated point-to-point link to every other device. The term dedicated means that the link carries traffic only between the two devices it connects. To find the number of physical links in a fully connected mesh network with n nodes, we first consider that each node must be connected to every other node. Node 1 must be connected to n-1 nodes, node 2 must be connected to n-1 nodes, and finally node n must be connected to n-1 nodes. We need n into n-1 physical links. However, if each physical link allows communication in both directions, we can divide the number of links by 2. In other words, we can say that in mesh topology, we need n into n-1 by 2 duplex mode links. To accommodate that many links, every device on the network must have n-1 I/O ports to be connected to other n-1 stations. And a mesh offers several advantages over other network topologies. First, the use of dedicated link guarantees that each connection can carry its own data load and thus eliminating the traffic problems that can occur when links must be shared by multiple devices. Second, a mesh topology is robust. If one link is unstable, it doesn't incapacitate the entire system. Third, there is an advantage of privacy or security. When every message travels along a dedicated line, only the intended recipient sees it. Physical boundaries prevent other users from gaining access to messages. Finally, point-to-point links make fault identification and fault isolation easy. Traffic can be routed to avoid links with suspected problems. This facility enables the network manager to discover the precise location of the fault and aids in finding its cause and solution. And now the main disadvantages of the mesh are related to the amount of cabling and the number of I/O ports required. First, because every device must be connected to every other device, Installation and reconnection are difficult. And second, the sheer block of the wiring can be greater than the available space. That is, in walls, ceilings, or floors can accommodate. Finally, the hardware required to connect each link, I/O ports and cable, can be prohibitively expensive. For these reasons, mesh topology is usually implemented in a limited fashion. For example, as a backbone connecting the main computers of a hybrid network that can include several other topologies. One practical example of mesh topology is the connection of telephone regional office, in which each regional office needs to be connected to every other regional office. And now let's move on to star topology. In star topology, each device has a dedicated point-to-point link only to a central controller, as you can see in this diagram. And this central controller is usually called as hub. The devices are not directly linked to one another. Unlike a mesh topology, a star topology doesn't allow direct traffic between devices. The controller acts as an exchange. If one device wants to send data to another, it sends the data to the controller, which then relays the data to other connected devices. And a star topology is less expensive than a mesh topology. In a star, each device needs only one link and one I/O port to connect it to any number of others. This factor also makes it easy to install and reconfigure. For less, cabling needs to be housed, and additions and moves and deletions involve only one connection between the device and the hub. That's all. Right. So other advantages include robustness. That is, if one link fails, only that link will be affected. All the other links remain active. And this factor also lends itself to easy fault identification and fault isolation. As long as the hub is working, it can be used to monitor link problems and bypass defective links. One big disadvantage of star topology is the dependence of the whole topology on one single point, the hub. If the hub goes down, the whole system is dead. Although a star requires far less cable than a mesh, each node must be linked to a central hub. For this reason, often more cabling is required in a star than in some other topology, for example, ring or bus. The star topology is used in local area networks and often use a star topology with a controlled hub. And now let's move on to the next topology called bus topology. And this is the diagram which shows the bus topology. And the preceding examples which we see earlier, they all describe a point-to-point connection. Bus topology, on the other hand, is multipoint. One long cable acts as a backbone to link all the devices in a network. Nodes are connected to the bus cable by drop lines and taps. A drop line is a connection running between two devices and the main cable. A tap is a connector that either splices into the main cable or punctures the sheathing of a cable to create a contact with the metallic core. As a signal travels along the backbone, some of its energy is transformed into heat. Therefore, it becomes weaker and weaker as it travels further and further. For this reason, there is a limit on the number of taps a bus can support on the distance between those taps. Advantages of bus topology include ease of installation. Backbone cable can be laid along the most efficient paths, then connected to the nodes by drop lines of various lengths. And this way, bus uses less cabling than mesh and star topology. In a star, for example, 4 network devices in the same room require 4 lengths of cable reaching all the way to the hub. So in a bus, this redundancy is eliminated. Only the backbone cable stretches through the entire facility. Each drop line has to reach only as far as the nearest point on the backbone. And disadvantages includes difficult reconnection and fault isolation. A bus is usually designed to be optimally efficient at installation. It can therefore be difficult to add new devices. Single reflection at the tops can cause degradation in quality. This degradation can be controlled by limiting the number and spacing of the devices connected to a given length of the cable. Adding new devices may therefore require modification or replacement of the backbone. In addition, a fault or break in the bus cable stop all transmission even between devices on the same side of the problem. The damaged area reflects signal back in the direction of origin, creating noise in both directions. Bus topology was one of the first topology used in the design of early local area networks. Ethernet LAN can use a bus topology, but they are less popular now, and for reasons where the bus topology is overcome by ring and other hybrid technologies. So now what we are going to see about is ring topology. In ring topology, each device has a dedicated point-to-point connection with only the two devices on either side of it. That you can see in this diagram. So a signal is passed along the ring in one direction from device to device until it reaches its destination. Each device in the ring incorporates a repeater. When a device receives a signal intended for another device, it repeats and regenerates the bits and passes them along. A ring is relatively easy to install and reconfigure. Each device is linked to only the immediate neighbors. To add or delete a device requires changing only two connections. The only constraints are media and traffic considerations. In addition, fault isolation is simplified here. Generally, in a ring, a signal is circulating at all times. If one device doesn't receive a signal within a specific period, it can issue an alarm. The alarm alerts the network operator to the problem and its location. However, an unidirectional traffic can be a disadvantage here. So, in a simple ring, a break in the ring, such as a disable station, can disable the entire network. So, this weakness can be solved by using a dual ring or a switch cable of closing of the break. Ring topology was prevalent when IBM introduced in its local area network. Token ring now today, the need for high-speed LANs has made this topology less popular. And there is another topology called hybrid topology. And a network can be hybrid. That is, for example, we can have a main star topology with each branch connecting to several stations in bus topology. Thank you.